In this video, we're going to begin to talk about the conservation of momentum. And when we talk about an isolated system in which a collision is occurring, momentum is going to be conserved. And what that means is the momentum at the beginning, so the initial momentum, will equal the final momentum. A collision is just the result of physical contact between two objects, and this contact that we're speaking of can be either physical contact or it could be an electrostatic interaction of electrons in the surface of atoms of bodies, because when we view two things of being in contact, we view them macroscopically as touching when really they don't actually touch. The electrons in the outer shells of each object repel each other, and there isn't that true contact of what we think. And so we just want to make sure that this electrostatic interaction can also be considered this contact that we speak of on a macroscopic level. Another key point is that an isolated system will have no external forces. The principle of the conservation of momentum states that when no external forces act on a system consisting of two objects that collide with each other, the total momentum of the system remains constant in time. So what this means is that the momentum is going to be conserved, and specifically the momentum at the beginning will equal the momentum at the end, or the momentum before the collision will equal the momentum after the collision. Looking at an example, let's say we have two objects, and we'll call one object 1 and the other one object 2. And these two objects move towards each other so that they collide, and then after the collision they fly off in the opposite direction. Well, looking at the collision, 1 is going to exert a force on 2, and 2 is going to exert a force on 1. And that force is going to be a variable force, and in this graph pictured over here to the right is an example of what that force could look like. And if we look at this graph as force as a function of time, we know that the area under the curve is going to be the impulse. And we know impulse means change in momentum. So what's going to happen in the collision is that object 1 is going to have a momentum moving to the right, but then after the collision it's going to have a momentum moving to the left. And then in object 2 it's going to have a momentum moving to the left, but then after the collision it'll have a momentum moving to the right. So the momentum of each object will change, however the total momentum of the system remains constant. And we can see this looking at each force graph. The force of object 1 on 2 is going to be positive, and the force of object 2 on 1 is going to be negative. Now, it doesn't really matter which one's positive, which one's negative. What the key is that the forces are equal but opposite. And if you see, the area under the curve of this one is going to have a positive area, and the area under the curve of this force is going to have a negative area. This means the impulses are also equal and opposite. Let's look at this situation mathematically here. And if the impulses are equal but opposite, that means the impulse of 1 on 2 is going to equal the negative of the impulse of 2 on 1. And so we know impulse is just equal to the force of 1 on 2 times delta t, and that's equal to the force of 2 on 1 times delta t. And we know impulse is equal to the change in momentum. How do we find change in momentum? Well, we take our final momentum. So if we have, this is the force of object 1 exerting on 2, so this is the change in momentum of object 2. So it has a final momentum, and we subtract its initial momentum, and we know that that's going to equal the opposite of the change in 1. And so if we do a little algebra here, we can take this initial momentum here, and since we're subtracting, we can move it over to the other side, and then we can take this final momentum here, since it'll be negative, move that over to the other side, and then this negative will distribute through to this negative here to make it positive, and we get m1v1 final plus m2 v2 final is equal to m1 v1 initial plus m2 v2 initial. And what does this tell us? This tells us that the total momentum of the system at the end is equal to the total momentum of the system at the beginning. And this shows us that the momentum is conserved. So the formula that we are going to hold to in all of these collisions is that the initial momentum is equal to the final momentum, and that's the momentum of the system. And so the momentum is conserved for the system of objects, not necessarily for a single object, but for the system of objects, all the momentum is conserved. This system includes all of the objects interacting with each other, and assume only internal forces are acting during the collision. And we can generalize to any number of objects. Let's look at another example here. And let's say, starting from rest, two skaters push off against each other on ice where friction is negligible. One is a 54 kilogram woman and the other is an 88 kilogram man. The woman moves away with a speed of 2.5 meters per second, and we want to find the recoil velocity of the man, meaning what is the velocity of the man? What's this right here? What's his velocity moving away? Even though this isn't necessarily a collision, these two skaters aren't colliding, we can still treat this as an initial momentum and a final momentum. So the momentum that we have here initially is going to equal the momentum we have here in our final situation after the interaction. Looking at the conservation of momentum, we know that initially when they're together, their momentum is zero. There's no momentum because they're not moving. Both skaters are stationary, so their velocities are zero. So that means the final momentum is going to equal zero. And so using that, we can solve for our final velocity that we need, which is the velocity of the man, or in this case we're calling VF2, and then plug in all of our given information. Now, when we do this, we see that we have a negative sign there because we're subtracting over this momentum from the woman. And in the end, we get a negative 1.5 meters per second. Well, let's make sure that that makes conceptual sense, in that if the woman's velocity is 2.5 meters per second and it's positive moving to the right, that means that the man's velocity is in the opposite direction. And does that make sense? If two people are pushing away from each other, would they move in opposite directions? And yes, they would. And so we do need to have a negative velocity for the man. Another way to look at this is that in order for the momentum to equal zero in the end, the momentum in one direction has to equal the momentum in the opposite direction. And in this case, we do have that. When applying the principle of the conservation of linear momentum, we want to follow these simple 4 steps here. In that, first, we need to decide which objects are included in the system. Okay, and it's important to identify the system, what's included in the system, what's not included in the system. Then, relative to the system, identify the internal and external forces. Remember, for an isolated system, we can't have any external forces. And so we need to verify, is our system isolated? Are the forces going on only internal? And if they're only internal, then we're okay. But if we have any external forces, then our system's no longer isolated and we can't assume that the linear momentum is conserved. And then finally, set the final momentum of the system equal to the initial momentum. And remember, momentum is a vector, and therefore direction does matter. So momentum to the right we typically say is positive, momentum to the left we typically say is negative. Now you can change that convention. That is not set in stone, but you need to pick one is positive, one is negative.